Chevron out of the Houston office. We're going to talk about a brilliant thing about operational science and capital projects. Those of you who are on Tyson may have had some similar courses. This is kind of a skew on the next generation project. For you, Nicholas, and Jim.
Hey, y'all, thanks for hearing me. You don't hear me? Thanks for having us today. So, as indicated on record, it's been a little long. Managed to get 4 years in 5. Quite nice that time. But graduated mechanical engineer, we do a little bio of ourselves. Mechanical engineer has been in many different industries, mostly around engineering and construction. Worked for companies like Brown and Root, worked for companies called Enron, manufacturing companies, and then most recently Chevron. So most of my career at Chevron overseas, executing big major capital projects, and never thought I'd be in the places I've been. And the past 2.5 years, I've been actually in dairy farms, trying to help with the energy transition, delivering projects, renewable natural gas projects. So capturing manure on the back of the dairy farm and taking gas off of it and sending it to market, mostly in California. So we've been doing this operation science for a while. I'm gonna let Nick introduce himself, and then we'll get into it.
Yeah, so my name is Nick One, class of 2005, which I'm realizing maybe probably not even born, maybe whenever I was here. Yeah, so civil engineering, I did grad school out in California. My objective was to do high-rise buildings and seismic zones, so my focus was on structural engineering. As I was getting out of school, the best job offers I was getting was doing offshore platforms. And so I came back to Houston to do offshore platforms for a couple of years, got involved with Chevron, and have had the opportunity to work a number of places. So Gulf of Mexico, West Texas, Russia, India. So actually the first time I met Jim, he hired me. So Jim was the engineering manager on what was the largest project in the world at the time. Not just for Chevron, but like of all companies. And Jim brought me over to India to oversee part of the India office, and we had 2,000 engineers and designers working on a single project in India. So that was the first time. That was the first time I was introduced to this topic. Like the first conversations we had is, welcome, learn this stuff, and this is going to be what's next.
So with that, we hear some of you guys got to leave pretty closely at the end of the class, so make sure you get your questions in early before you leave. It's a dialogue. We'll save some time for questions, but if you want to ask a question while we're talking, please stop us. It's much more engaging for us if we talk the way we go. So I guess the question is operation science and why does Chevron put this in their project management? And so what we're going to do is we're going to talk about the why. We're going to talk about how you go about designing the system, and Nick's going to show some simulations that he does that helps us make decisions in our project execution. And then we're going to talk a little bit about controlling the system, which is a little bit of controlling the work and the tools we use and how you use the data coming out of that. The good thing about this is that what we're talking about here, it doesn't matter what you do when you get out of school, you can apply this to anything. If you're a design engineer, if you're a barista at a coffee shop, whatever it is, some of the terms, some of the things we talk about. Because everything we do in life, there's a production system associated with it. If you start looking at the production system in a way that everything happens, you understand why it starts to slow, right? Why am I not getting the information I need, and all those type of things. So a lot of the industrial engineers in here probably know this already, and y'all can teach those few things, but we'll start going through it. So the why we did it is because if you look at the engineering construction business itself, it has done very little to improve productivity over the lifespan since about 1950. And so you can see the other industries have really taken an uptick on how well they produce products coming out of their system, right? So if you look at it, you can see the manufacturing, the big blue line, is kind of what underpins operation science and how you look at projects. And so we thought, hey, this is interesting for a Chevron perspective. We should learn sometimes to apply best practices. So we went on a journey a long time ago, 2016, full time since then. It's been hit or miss about how well we can deploy based on the projects we're working on. And we had a few spot ones even earlier than that, where we applied some of the control of the work to help manage the work going through the production system. So that's kind of a why, because right now, the industry you're about to struggle to get projects done. And it's even more of a struggle now with some of the places that we're even operating, like in dairy farms in Iowa. You know, capacity's not there, capability's not there, so you start looking at things in production systems, you hopefully have a better outcome for you. So, again, the industry you're going, and it's not a company problem. A lot of times we look at Chevron and say, oh man, Chevron's terrible. But you look at the industry, all our competitors, everyone struggles in the same thing. So just real quick, what is operations science? There's a guy by the name of Mark Spearman, who used to teach here a long time ago. He put a book out called Factory Physics. A lot of that underpins this. But it really is looking at your project as a production system, right? Putting that system thinking to it. There is some science to it, you know? So there is, which Nick loves this stuff, there's the Kingsman equation and Little's law. And we'll talk about that. Little's law takes about WIP, which is work in process. And work in process can be anything from, if you're an engineer, designer, you're doing drawings, that stack of drawings on your desk. That's called work in process. Going and buying equipment because you want to install early, like a construction project. That's called work in process. So these are kind of the equations that underpin it, you know, to help us make decisions as we look and model systems out there in our projects.
Yeah, you might, right. So we don't have to talk about all the science and equations and all that, but the curves, you can recall these relationships, you can apply these to just about anything. So the one on the left, like you said, is Kingman's equation, describes the relationship between resource utilization, so what percentage of the time is a resource being used, and cycle time. So as you try to do too many things at once, things take longer, right? So this is why it takes you longer to get home during rush hour, or maybe why you avoid the lunch counter during that kind of lunch rush. It's because of this. And then the other piece of it is the impact of variability, right? So if we take the driving on a highway example, it's a very highly variable system, distracted drivers, drunk drivers, mechanical breakdowns, animals out in the road, right? Now, maybe fast forward 30 years, we're all driving Teslas on autopilot or something. You know, we've taken out a lot of that source of variability. We can potentially get home back, right? That's kind of the basic principle. And then the one on the right is kind of a variation, right? So these are, as you add work to the system, you can get more out of the system up to a point. And then it hinges over and you can't get any more out. You've reached the capacity of the system. And what happens at that inflection point is the cycle time just starts to take longer. So it just starts to take longer to get things out of the system. So that's the 30-second version of that.
So again, here's a picture of what we call work in process. Being in construction industry, you see a lot of times, hey, buy this stuff, get it to site, and then we'll be ready to install it. Well, what happens is this is work in process. You saw that curve, more work in process, the longer it's going to take to get the project done or the activity done. And what is this right here? This is stranded capital. At one point, Chevron, I was in the board on that. We had $1 billion in stranded capital across the board. Just equipment, pipe, materials. So not only is this capital that is taken, but also you got to preserve it when it's out there. You got to find it when it's time. And a lot of times the material gets lost. And what are you doing? You're repurchasing it again. And you're going to the whole system again, which is again capital, more money to get something done.
Or maybe a change order comes and now all of a sudden the thing's working.
Exactly. Here's another one, right? Sometimes a good idea. Let's put this pipe in. We didn't have any valves. So they built these spacers to put in place in the valves so you can at least get the piping done. But then what are you gonna do? You come back later, you got the valves, right? There's money to do this, and then there's money later to come reinstall these valves. So again, we're trying to look at and make better decisions when we do our projects, not a just in time like manufacturing, but making very pointed decisions on how much work in process do we want to have, so we can look at how we get our projects done for us more predictably is what we're doing. So why, you know, if I went through the why a little bit, again, it's looking at a project as a series of production systems. You're saying, Joe, what are you talking about, a production system in a project? Well, engineering is a production system. Procurement is a production system. Logistics is a production system. Fabrication, construction, systems completion, turning the project over. Within engineering, what do you have? Well, you have mechanical discipline, you have HVAC discipline, civil. All of those are in production systems, intertwined with each other. And you really want to understand how they're reacting to each other so you can remove the variability. And with it, there's kind of 5 levers that you have that you can pull back and forth and make decisions on. One is around scope, which is what am I designing, right? Where's my project? my supply chain look like? And making decisions that help support the execution of that and design of that facility. And with that, you also have the workflows. Again, understanding how the work is flowing to that production system. We had, give you an example of the project they were talking about, we had loop diagrams. And I asked an engineer at Farnborough in the UK, we touched the UK, we touched Houston, we touched England. I said, how many steps did it take? He said something like 27 steps to get this drawing all the way through starting, all the way to issue for construction. I said, great. So we spent 3 weeks mapping out the workflow. How many steps to work? Was it 122? So like 122 steps through 3 different offices to get a drawing out. And you can see where you may have a little bit of variability in this communication trying to get things out. So again, understanding the workflow of those production systems is important. Understanding the capacity. How many people do I have? What's the laydown in my yard that I have? Right? I mean, capacity can be anything. What's my equipment that I need to be able to get this done? So understanding that capacity, again, to help model that system, make decisions is important. Inventory, we talked about that already, and then variability. Variability is one of the biggest things out there that really impacts predictability of our projects. And in the past, what Chevron used to do in our old management system, we would design, schedule a project, and assume no variability. Nothing bad was going to happen. We applied all the best lessons learned possible from all the previous projects. Well, at the end of the day, projects are not unique, but you do have the same problems. But at the end of the day, you can't apply a lesson learned for a $50 million project, the same lesson learned for a $10 million project or a $1 million project. So, again, understanding the variability out there is a huge way to help make our projects more, or trying to use it to make our projects more good. And again, how do we use it? We have very different groups in Chevron. We have a group called opportunity shaping, which kind of takes and shapes the opportunity in the project, let's say the business development, and they use it to make decisions around what's the size, what are we going to do, what's the execution strategy for this, testing concepts. Then we also have engineering. Again, they got to do the design. So they need to understand where's this project going to be, what are the design conditions, what does the supply chain look like? What kind of materials can I use out there? Am I going to stick build it? Am I going to modularize it? So all those are site-dependent things you understand. We have supply chain, where the materials coming from. A project we talked about Kazakhstan, we bought almost every piece of equipment in Europe. We shipped all the equipment from Europe all the way to Korea, put it in modules. We took the modules all the way from Korea and took them all the way back to Kazakhstan. You can imagine there'd be a little bit of variability. You may have a few pickups along the way. Called variable pickups along the way. That would make our project a little less predictable. Construction, again, understanding the workflow, how's the supply chain, how the materials getting to the site, and understanding that, as well as engineering deliverables, understanding how the work is getting done. A lot of times we like to open up workspaces, a lot of workspaces, be it underground piping, putting underground electrical, then we start foundations, and then we start pipe racks, so all this different construction. What happens is that you get the weight of each other, right? Which again creates a lot of variability, right? And then what do you have with that? You have a lot of work in process. Learn about curves, work in process is definitely increases throughput. And then the data digital piece is hugely powerful. We haven't quite figured out because our data, we don't do a good job at Chevron. A lot of the companies are using the data yet. A lot of data is not very have patience, please. So we do use the data to make decisions and try to apply to other projects about what variability is out there. Who's still variability in this project. We even have scenarios where we see the same variability comes up and put in ways to mitigate it. So again, these elements are very powerful for us. And then the how. Again, I talked a lot about this in our execution planning. Delivering sequences, looking at to understand how the work gets done, and the impact it really does help us execute projects and define projects and a little bit. So with that, I think let's go over to Cindy. You want anything on here?
Yeah, no, I think we're good.
Yeah, I think a key word up there that I look at is condition precedent. I don't know if you guys, we've done a lot of this work with condition precedents because schedules are really good to put milestones out. So a lot of times you get teams aligned, and especially engineering management, really get the conversation back to using conditions precedent, what decisions need to be made before I can advance this work product to the next level, or what decision needs to be made. I'm sure you guys are doing that in your life every day. You want to do a condition to go move someplace, or whatever you do, I mean, a job, a house, all these other things, right? And so thinking about conditions-based execution, no matter what your competency level is in project execution, really helps to bring it down to a foundational level and get people thinking about what needs to be done to be able to make a high quality decision, and the people in the room to be able to apply it. I use this quite a bit in my renewable natural gas projects, because I'll do a lot of different capability and capacity and on the farm sites. It really helped bring down that conversation where everyone's on the same page, so we can advance the work safely and be able to be ready. Go ahead.
All right, okay, I'm about to switch on to, how we design a system. Any questions before we do that? Okay.
Done? I see a hand. Yes.
Okay, so you were talking about how you map your workload. I don't know if that's part of designing the system, but could you go into more detail after mapping it? How did you reduce that, like, work in progress? Because it sounds like you had a lot of crossing lines.
That's perfect. We're about to go into that right now.
Exactly, yeah, it's exactly.
It's designing the system.
Yeah.
That's perfect. Thank you for the question.
All right, okay, I'm gonna actually switch into a simulation software that we use. I think you guys probably use this software or something similar for the industrial engineers. There are equations for all of this stuff, right? So that you can use an analytical model where you just rearrange the equation to solve for the variable you're looking for. I find that simulation model helps people understand these concepts, so that's what we use primarily, although there are very powerful analytical models. They're much faster, but
It is. It's Simio, damn it.
okay, so this is going to be an example. Let's say we're building an
That's
office
good.
building, and we are responsible for outfitting the office, right? So they're gonna.
I guess
frame
I
up the
understand
office
it
with
the second
studs, right?
time,
And then
but
we gotta come in. We're going to do the rough in electrical. We're gonna do the rough in HVAC. Then we're going to put insulation and drywall, paint the walls, do the finished electrical, so light switches and light bulbs and things like that, and then we're gonna install the doors. All right, so this is like a map of the system. This is what we're talking about when we're talking about building a map of the system. Okay, in order to do all of these steps, we need people, right? So here's our people. So I got electricians and drywall people. In fact, I can even only 3D view, they look like people. And so those are all the people that I'm going to use to do this. And each one of these little boxes here represents a step in the process. And we talk a little bit about variability, and that's important here because whenever you do rough in electrical, for example, it doesn't take exactly 3 hours every office. It'll take somewhere between 1 and 5 hours. Right? There's going to be some variability, and that's really, it turns out to be a really important piece of this. And so we explicitly model all of those pieces of variability, right? And we don't know going into this exactly what that's going to be, but we can usually bookend it somewhere. And so that gives us some feel for the variability. So we'll go into that more in the next example, but this is an example. So let me hit the play button here and you kind of see what's happening. Let me hit the pause button. It's moving. Things are moving really fast, right? But each one of these green triangles up here represents an office as it's making its way through our production system. And when they're on top of the box, that means that we're working on it. And when they're over to the side, that means they're waiting to be worked on. So we only have one electrician right now, and so he's busy. And then you can see our people, right? There's our resources. And when they're green, that means they're busy. So these two guys are working on this office. And when they're blue, that means that that they're waiting for work. So you have people waiting for work, and sometimes you have work waiting for people. That work waiting for people is that whip concept that we talked about earlier. Okay, with a simulation model, we can, it's choosing a bunch of random numbers in this according to the parameters that we gave it, and we can start to learn some things about it. So a couple of the charts that I have trending here. One is just the utilization of the electrician. So it's like 99% utilized, if you can even see that. I've also got average cycle time, so how long does it take on average for an office to make its way through the system? And then throughput, how many offices per day are leaving the system, not entering the system, but leaving the system. And then I've also got over here the lines of balance, which is just blue line is number of offices that we started, and the red line is number of offices that we finished. And so, I meant to start on this one. So, these are backwards, sorry. This one goes to this curve, this one goes to this one. So, that's why the right piece. Okay, so what are we seeing here? Number one, we're seeing that we're starting offices faster than we're finishing, right? So those two lines are not parallel. And so the question becomes, okay, where is this work building up? Well, in a model like this, we can actually see it, right? So we can see all of this work building up in front of the electricians, right? So I've got rough and electrical and finish electrical. The electrician has to do both of those things. And so we can just see where is the work building up, right? You could do this same thing on the subway, sandwich shop, or any type of production system that you have. We did, the laundry. I got 4 kids. We did this on the laundry system at our house, and so you can do this type of thing. Okay, so where is the work building up? There's where it's building up, and so we know we have a bottleneck, and we know where that bottleneck is. Every system has a bottleneck, but it's really helpful if you know where it is, because if you don't like the result, you know exactly where to go. And so in this case, I knew that the bottleneck was my electricians, and I can also see that because of the utilization of that electrician. If you'll remember way back a few slides ago, we talked about the utilization of a resource and cycle time. This is that playing out right here. Okay, so that's why I have this other model. The only thing, I just made a copy of it, and the only thing I changed here was the number of electricians. And so, so you can see the impact, right? So number one, my electrician's not as highly utilized. We're still 85% or so utilized, but all of a sudden I'm able to keep up with the work. My cycle time is significantly lower, and my throughput is higher. Now, throughput being higher, you would kind of expect, oh yeah, you throw more people at it, of course your throughput's going to go. But anyway, all of these other kind of interesting pieces of this can provide very valuable insight into how you're going to make the system perform. Okay, all right, so that's a kind of a cartoonish example. Let me go to a real world example that just like last week I was working on this with the team. All right, so this is an engineering management example. So I know this is engineering project management. In our world, we think of project management and engineering management kind of as a separate thing. So this is the engineering manager, so the person overseeing the engineering on this offshore platform, was looking for some help to make sure he was going to meet his objective. So this is an offshore platform. Hopefully you've seen at least a picture of it. Some of you may have even been on one. If you look real close, you'll see a whole bunch of pipe. We build the structure out of pipe. We build, or at least a lot of the subsea of the structure out of pipe, and then all of the process pipe is in there. What is on the right here is obviously an extract of the 3D model, but this right here is what's called an ISO diagram. So some of you may know this, but this is one of the key deliverables out of engineering, so that the fabricator knows how to build the thing. And so it's got dimensions and all kinds of information. All right, this particular project is going to be built in Korea, similar to the other one. The Koreans are very good at what they do, right? And they've optimized their system, and they depend on you as an owner to make sure that you are providing engineering in a way that is optimal for them. And so in this case, they have an obligation. The engineering and owner has an obligation to provide 200 ISOs every 2 weeks, so 100 per week. That's their objective. And if they don't, then the Koreans will, anytime they miss that, there will be a change order, and that can cost significant amounts of money because they're very good at designing these contracts to do so. So it's very important that these guys meet their objective of 100 ISOs a week. Okay, so that's kind of the setup for this. All right, so 2 weeks ago, I was in the engineering contractor's office, and we did a kind of a process map, and this is what they had drawn for me. And so we're primarily concerned at the space between this line and this line over here. So there's a prep step where they prepare the model for extracting the ISO. Then there's a check step where somebody sits down and checks the thing. A scrub step, so they pick up all the comments from the checker. Then there's a back check of the scrubbing to make sure they actually got all the comments. Then there's a QC check, and then it goes on to document control for the issue. So that's the basic process. They also provided some information on how many resources they were going to have working on this, and so we did a quick model of this. Again, just like the model I just showed you, we did a model of this. Now, if you were doing this kind of traditionally, you would say, probably do a calculation like this. So I've just taken that check, so the check and the back check step, it takes on average about an hour and a half. And so if we were going to try to figure out how many people do we need, we would say, okay, hour and a half for ISO, that means I can do 5.3 per day or 26.7 per week. Therefore, if I've got to get 100 per week, I need 3.7 people, or round it up to 4. And so that's the way you do that. Now, the problem with that is, even though we didn't assume that every ISO takes the shortest amount of time, we acknowledged that there's variability, so we took the average. But what we did is we eliminated the variability. We said every ISO, in that calculation, every ISO takes the same amount of time, the average amount of time. Okay. Anyway, that's like, you were doing this traditionally, that's the result we would come up with. And that's what they came up with too. And so, anyway, this is where the model came in. So I ran that scenario through the model with 4 checkers, and I get a curve that looks like this. So this is, again, that throughput versus width curve. So here's what that system could do, assuming we had no variability, assuming every ISO took the same amount of time, and it was the average amount of time. So, we can see, we can do up to probably 130 ISOs per week, and that's way more than our 100 that we're looking for. Okay, so in their mind, that kind of validated their assumption, or their conclusion. However, when we incorporate that variability, we see a much different curve. In this case, the model actually suggests they can only do about 81 per week. And we can see our optimal whip level, kind of where that happens to be, which we can go into that later. But what this was telling them is, okay, actually you can't actually meet your objective with this production system, with these set of resources. You just simply can't do it. You can yell at them, you can do all kinds of things, but the system, they can't do it. It's not their fault. They simply can't do it. And so the next question then obviously becomes, okay, well, I've got to get 100 per week. So what do I do? Okay, well, let's first find out where the problem is. And so we can look at where's the work backing up, right? And so we see it's primarily in front of this check and back check step. And we can see our checkers are 98 and 99% utilized. So that immediately tells us this is where the bottleneck is. This is where we need to work if we want to try to improve this. Okay? So what are our options? Okay, well, one thing we could do is, what if we could reduce that variability? All right. In this case, on average, it takes 75 minutes, so an hour and 15 minutes to do the step, but it might take as little as 45 minutes, or it might take as much as 4 hours, right? So that was the wide variability that these guys had. They said, okay, look, what if we could improve that, right? How much of an impact would that have? And it gets us much closer, right? If we had, the red line is 3 hours. If we kept our average the same, but we just reduced our maximum to 3 hours, or even to 2 hours, that's the blue line, right? So all of a sudden now our objective seems to be within reach, and we haven't spent any more money. We haven't brought any more resources or anything. We just said, look, what if, we haven't said how to do that, but we said if we could reduce the variability, how much of an impact would that have? So that's kind of the result of that sensitivity, right? The other option is we could add people, right? And so we could add, this is what it looks like if we add another person. And so with a 5th person, it looks like it's possible to do that, but we would get right at the limit, right? So what this means is we could achieve it, but our resources would be like 98% utilized. So we're like right on the edge. Maybe we would do it, some weeks we won't. And so that's not a very safe place to be either. And so with these two kind of parameters, I went and played with some sensitivities. And so this kind of big square on the left is, what if we kept our variability the same at 4 hours? This is with 3 hours, and this is with 2 hours. And how many checkers would I need in each case? And so we can run these sensitivities and say, look, if we really want to do this and we don't think we can improve the system at all, you're probably going to need 7 checkers, right? In this case, they think they can get it down to 3, and so the recommendation would be to use 6 checkers. Now, with 5 checkers, the resource at the highest utilized resource is only 86%, and so that's kind of where they want to start. But what we're going to do is we're going to start tracking them, and if we see them start to veer off, then we're going to immediately know what to do to actually fix that. And we've done this. We've done this on other projects, and we've done this analysis, and they said, thanks, but no thanks. We've been doing this a long time. We know what we're doing. And it was just almost dead on with what we predicted is what and so 6 weeks later, they ended up having to add resources. Okay, so that's a very,
So real quick, so what? Why does this matter? Go ahead.
I mean, it's gonna help you save money in the long term. So you can stay closer to project timeline, you can budget more accurately for what you're actually completing. You're not gonna have to play with resources within the project if you can properly predict what you're gonna need.
That's exactly right. Because at the end of the day, when you're an owner, right, you own all the risk of the project delivery. You're paying an EPC, an engineering procurement construction contractor to deliver something. A lot of time, these contracts, at least in the Chevron world for engineering, is a reimbursable contract. And so that means we pay for every man hour and every person on the project. And so not only do we have risk of delivering deliverables, piping ISOs, whatever it is, to a fabricator or a construction contractor that would come back with it, but we're also paying for resources. So we want it predictable so we can meet our contractor requirements, but we also want to make sure we have proper resource utilization so we don't pay too much. We want some extra, of course, we want some extra capacity because a human, I mean, when you're at 110% capacity, you can't get anything done, right? So that's why Nick was saying, like, there's a number between 80 and 75% that you can absorb some extra work if you need to. It doesn't disrupt a potential production system or yourself or you're doing during the day. So these type of things, the so what is when you're out there, you're going to be managing this kind of stuff. Maybe not initially, but at some point you will. Or you may be managing a team, or someone may be managing you to get something done. And so again, these tools and these principles can be very useful for you to have a conversation to help manage your day, your work, your contractor, whatever it is very helpful for that. And to know where the bottlenecks are and know where you gotta put resources is hugely important. Because a lot of times they say, no, I need a pipe stress guy. They check the stress to make sure it's within the guidelines. Like, no, that's not where my problem is. My problem is the checker. My problem is document control over here. Or you may even get the thing where my problem is translation. Because in Kazakhstan, we had to have all our drawings that went to the field translated into Kazakh and into Russian. You can imagine the variability you have in that. Right?
Yeah, just the confidence that as an engineering manager you can have by knowing knowing how your system is going to behave. It gives you much more confidence than just, doing some math, maybe throw a productivity factor on it and say we should be good. It's better to know you're going to be okay than to assume you're going to be okay. Okay, that's all I had in terms of kind of like the technical stuff. I'll pass back over to you for.
You want to show the wall factor one?
We can if you want.
Yeah, show the wall factor one.
Okay.
I think that's an interesting one in the fact that the well factor is a lot of people hear about shell, full baby drill, all these different things, right? About bringing more oil to market. But again, you still have the same principles you want to manage when you're developing either a big shell environment where you drill a lot of wells, or maybe this is actually in Saudi. And so we have big operations over there. We're trying to figure out what do we do to develop this thing? How fast do we develop it? Everybody wants you to develop it really quickly, but at the end of the day, there's got to be a certain pace to be able to do it predictably as well as to do it cost effectively.
Yeah, so this model is a project that was in early phases. So we weren't even designing the system yet. We're just figuring out, okay, what kind of a system do we want? How fast do we want to go? Exactly the Jim's point. Okay, so this is just a video I'll kind of talk through. So Mike should have taken some names off, but that's okay. All right, so in this case, each one of these triangles represents a well, and so this is a steam flood. So what happens is you drill a production well, and then a year later you drill an injector well that serves 4 of the surrounding production wells. So you inject steam, and that helps this heavy oil kind of loosen up and move to the production area. All right, so you drill the well, then a year later you drill injectors, and then it'll produce out of that reservoir. And then in this particular field, in year 7, I think we recomplete the well into a different reservoir, and we produce simultaneously out of both of them for 3 years, and then the first one dies, and so we continue to drill out of those. And so in this case, we're simulating the life of this field. And then, and we also have some observation wells, which aren't all that important, but yeah, okay, so we're simulating this in production. We have variability built into the drilling process, and so we say, okay, look, we're gonna pop a well on average every 9 days, pop a well, turn a well on every 9 days. But it could be as low as 7 days, or it could be as high, and we get the rig stuck, it could be 30 days, right? And so we model in all that variability, and then we simulate, in this case, we simulated over 5,000 wells over the time period, about 150 years. Just it took about 45 seconds to run the model. And we can aggregate all of the information about each one of those wells, look at what does our overall production look like, oil, water, gas, and then importantly for this guy, steam. Because then if we know how much steam each steam generator can do, we can then know something about how many steam generators we're going to need, how many water treatment plants we're going to need, and when we're going to need those. And then if we know how much that stuff costs, then we can get into our capital cost forecast. Here's how much we're going to spend over time, both CapEx and then operating expenses, which is the lower one there. And then it's just from there, it's just a hop, skip, and a jump to cash flow. So we can have a model of the entire production field and play with like very practical parameters. What if we, add another drilling rig, or what if we, we do some sort of quick change, and we can play with how that parameter manifests itself all the way to returns on this investment. Right? And so we can dial in what is the right pace for this development, and then we move into the next phase, which is okay, now designing the system that can do that. Okay, absolutely.
No, I mean, just many ways you can do this tool. And so even in West Texas, we're trying to, our mid-con business year, we're trying to deploy this a little bit more effectively because we spend a lot of capital in drilling holes. And we have what's called pop wells, which means put on production. We have a big queue of those things. We have a lot of work in process. And so we're working hard with them to try to influence and try to be able to get to more of a production system thinking. One of our competitors, Hess, does a really good job of this, and we learned quite a bit from them, and just through PPI and industry of how they go about doing this. And so it's super interesting if you can get that kind of production system into your development and into your wells and whatever you're doing, let it be, because you really can look at where you spend your capital and make your capital more efficient.
Yes, sir.
So those models require a lot of data. What is y'all's process for obtaining some of those points so you can put them up?
So like for that last one there, the type curve for what each well will produce comes from the geologist. That's something they produce anyway. When we're in early phases like this, we try not to like over-engineer this. Like let's not overthink it. Let's not pretend like we know exactly to the day how long it really is. That's kind of the beauty of having this variability as an assumption. Like we say, look, I don't know exactly. It's gonna be somewhere between here and there, and then we let the simulation do it. We do, we would do that model. So what you saw was a single replication of that model. We would then do 10 or 100, replications of that model and take average distribution. So when you're in early phases like that, don't over it.
But that is very interesting.
Oh.
But
Sorry. So now if we're in the previous one, the engineering drawing one. Okay. Now we've made these assumptions. Now what you do is you actually go measure this stuff. So every time, ideally, if I could convince them to do it, every time they would be recording all of that. So now I can then go back to my model with actual data instead of just my assumptions, right? So now I can update the model or refine that, and maybe my model length is moved, and so you get better information. Which is all of that data is what Jim's about to the source of that as well.
yeah, depends on how well you capture it and how well you can again show we're not that good at it yet, but we're trying as we learn. So the next part of this is how do you control the work, right? Once you've modeled it, once you kind of see how your production system is in play, at some point you got to control that work and understand what is critical variability for what. So if you're on a construction project, here's a fun fact, and you have 10 things you're going to do today, how many do you think actually get done? 3? Man, you're good. You must be an industrial engineer, Dave. So civil? Yeah, you're spot on. Usually about 30% of the tasks that you have planned at the end of the day get done. So what happens to the other 7? Tomorrow, you gotta get them done, right? And the 10 you're supposed to do tomorrow, they gotta get done, right? So So when we talk about execution control, it really is about trying to understand the work that's getting done today and tomorrow, understanding that work and seeing what variability is impacting it and being able to plan for it in that case. So here's some principles, it's very milestone focused. You're executing, we don't look like a week to 2 weeks out, even in engineering, you don't look that far out, even in construction. We have kind of daily planning in engineering, a week to 2 weeks, because it doesn't change as much as it does in construction. We commit to the work, we'll go through a little workflow here of what the daily, weekly planning cycle looks like. And then of course the analytics, we got a slide on analytics too. So,
You talked about finish the start.
finish the start. So scheduling tool, finish the start.
Yeah.
So,
Yeah, so if you limit yourself to finish and start relationships, you end up planning at a more detailed level. And so this is we will have a schedule. We still have a P6 schedule on all Chevron's projects. Our P6 schedule only goes down to about level 3, and then we do all of the detailed planning in something like this. And so we use finish and start relationships so that we can understand how all of that really ties together, and we don't have these you can have things that will overlap, but they actually need to pieces of them need to be done. So I think it kind of forces you to plan at a more detailed level. Just one element.
a little bit of condition precedent, gotta have this done before you start the next thing.
Yeah.
And that's really what execution control helps us do. So again, for execution control, kind of the cadence of what we do, we kind of have like Nick says, we put a P6 schedule out there, we do this high level milestone, where we think you might want to achieve something. We go through the standard process, that's kind of that mapping that Nick showed us earlier, and it's got an example we used, we thought it took 30 steps, and it took, 100, 200 steps to actually get work done. And that visibility is hugely impactful, not only for the owner's team, but also for contractors. A lot of times contractors understand what work needs to get done, to get deliverable out. So once we build the standard process, we start having a look at scheduling meeting, which looks out 2 weeks, could be 3 weeks. But again, things can change so much that we don't look out much further than that. And then from that look at scheduling meeting, we have what we call a daily week or work planning session. Like I said, in construction, we do it every day. We say, hey, here's all the activities you're supposed to do. You're gonna do it, yes. Engineering, say, here's what you're supposed to do this week. You're gonna do it, yes, and at the end of the week or the next day, we go through it, see what got done, what didn't done, what impacts that has to the schedule. And then, like I said, the very important part, what variability, what data we can collect to be able to manage the next day work or whatever it is. So again, you say you're gonna do it, you actually work, if you didn't, it all gets put back and look at scheduling as well as the planning.
I was just gonna look at, I think you may have mentioned this, but one of the kind of key elements here is you want the people as close to the work as possible to be the ones planning the work. This is not a project controls person back in the home office planning the work of the detailed electrician or whatever. This is the electrician, or maybe it's an electrician supervisor. Probably something like that. People as close to the work as possible planning the work. People are gonna do it are the ones that plan it, because not only do they know them, but also they're going to be more willing to commit to what they're going to achieve if they are the ones involved in planning.
I'll give you an example of the MTDE project that I worked on in the engineering office in the UK. So we had 2 contractors, we had Fluor and Willie Carson, they were joint venture together to form a company. We used Fluor processes, so we had Willie Carson people there too, plus we had a big agency contract. And so for them to understand what the processes were before was extremely difficult. And it's not like it's a shame on anybody, but it's very difficult to be able to understand what all the work steps are being drawn out. It's also very complex work steps because again, we had 3 or 4 offices, plus we had translation involved, and things they weren't normally used to doing, as well as it's almost like a professional area. I can't remember what they called it. What did they call it? They had stamped it by the Russian authority.
Oh yeah, expertise.
Expertise.
Yeah.
So a lot of different workflows that people don't understand. So getting people in the same room that's doing the work, understand it, is super important. Then we also had another project. We had 2 same projects on 2 different floors in the same office building, and the work is being done completely different. And so again, understanding, standardizing workflows, manufacturing, understanding the variability is hugely beneficial for making it.
The other thing I'll just real quick add is back to the mapping question earlier. Like most people know what they do on the project. they might know what the person immediately upstream of them does, and maybe what people immediately down, but very few people know like the whole workflow. And so getting everyone in a room to actually map that on the wall, sticky notes on a whiteboard type of thing, like just doing that exercise, even if you do nothing with the data, just having done that, you'll find value just in doing that.
So this is like some analytics we pulled from our block project. This is one of our dairy farms that we're doing up in California. And just look at some of the analytics we can pull from the tool and be able to make some decisions, right? So why not? You know, the reason summary, why work's not happening, what we talked about a lot from a variability standpoint. So if you keep looking at that, oh, priority change. Why is the priority changing so much on a daily basis? Well, because we're not planning our work. You can sit down and do some further exploration, make sure you understand what work activity needs to happen. You know? Equipment. Labor is insufficient. Okay, what labor do we need to bring in to make sure we're getting work done? So this one to me, I mean, there's a lot of other stuff. Root cause analysis, you know, root cause narrative, it's completed, not planned task, be able to give you insight of what you did was completed that was not planned. It's tied to that one variability. So you see, okay, we're not planning, sort of deep dive into that. And are we planning the right work, right? Are we in the right sequence? So a couple of things that we've used from this, from my standpoint, is they've been a project in Kazakhstan. We were doing a lot of lifts. And we couldn't do a heavy lift more than 15 minutes. 15 miles an hour. Yeah. So variability kept on coming out and saying, oh, yeah, when high wind, we keep trying to work, and we know when the wind's coming. So we ended up tying the tool to when you got calm. So we can get a better prediction of the wind and say, hey, I'm going to do this today. We're like, oh, no, you're not. So we're supposed to be going to be too high. Let's plan different work. So being able to use this analytics and tie different tools and different data sets out there is extremely powerful for us.
And just to point out, you mentioned the 30% number earlier. If you look at the orange line in the middle chart there, that's this team's, right? So they're up from like 80 to 85% probably on average, right? So by doing this, they're more reliably able to achieve the things that they say they're going to achieve. And the result of that is, if the schedule varies, which is on the left here, it's in red, but it is like, it's pretty steady, right? We're not losing a lot of days. But this is, every day we have data points. Did we move closer to our goal or not, right? So,
yeah, so the engineering management or project management or discipline management, whatever management you decide to go into, understanding these type of analytics, again, can help you navigate the risk that's on your projects on a daily basis. Again, I love to give another example, right? Again, you're the owner, you got a contractor work where we have 2,000 people in a global delivery center over in India. And we're trying to concentrate drawings on sea lifts because we have 3 sea lifts, 3 fabrication campaigns that we're working to. And we got, okay guys, no more working on the second or third sea lift drawing, we're only working on the first sea lift. We're getting this data like, oh yeah, we're working on the first sea lift, it's all we're working on. You start looking at the data, you know you're not, you're doing drawings in the second or third sea lift. Please stop that. You know, again, using your resources because you're paying for them and you're trying to meet a schedule for your contract or other contracts you have. Again, having data and being able to have that transparency is hugely beneficial.
So I'm just assuming here, but like construction projects like this are probably eventually contracted out to several different people. Like you'll have a contract electrician and stuff like that. The engineering design example you gave about having the ISOs, those are going to be like your design engineers are going to be on salary usually. So how do those two different analyses differ? Because like this is budget analysis, the other one's more schedule analysis.
yeah, so in the engineering one, that one is a contract as well. So we use contract engineering firms for that. So it's kind of the same from our perspective. But you could, even if it was our own resources, we would probably be even more interested in the utilization of our people to make sure that we are not, overworking people and we're not underworking people too, right? So that analysis can go both ways.
Yeah, I think that's a good question, right? Because the construction contracts are framed in different ways. It could be a lump sum, or it could be a time and material, or it could be a unit rate. Unit rate is you put this in pipe, you can pay for that, it covers all your overheads and all your costs. But regardless of the contract out there, especially with unit rate, you still want predictability. And you need to understand that because you want them to finish on time. Because if they don't, it's going to cost you more no matter what kind of contract you have. It's going to cost you more. And at the end of the day, what you'll learn is that the owner, as much as you wanna shed the risk and put the risk on your subcontractor, you own the risk. Every 100% you own the risk, every day, no matter what kind of contract you have. If you take that approach, which I've seen, a hands-off approach, thinking my contractor's gonna deliver for me, you know, because I got the right design base, and I got the right liquidated damages, I got all this stuff, and it's a failed model. And I know right now, in a lot of our new energies projects, because you have a different owner out there that's out there, you have a lot of investment firms, you know, you got a lot of private equity trying to bring on natural gas, or power, or hydrogen, all these different things, you know? And what they want is to shed their risk. And they shed their risk by trying to do a little bit of engineering, not much. Not a concept, you got lump sum EPC cost, liquidated damages on delivery, and it doesn't work. I've lived it through my Brightmark days and living it a little bit right now to hydrogen. It's a tough model, and companies are taking it because they don't have the experience, or they do have the experience, they think they can do it, or they want to get their foot in the door and be able to get the experience to do future projects, and it makes it very hard to execute that. Super hard.
We were just learning this stuff on FGP.
Right?
FGP was what, $10 billion over budget? I don't know, something like that. It was massive.
I mean, the oil and gas companies have learned, you know, how to try to structure their projects from a contractual standpoint. Reimbursable engineering, get the engineering done right, get it well matured, get your estimate, get your procurement plans and your construction plans, and then go and bid your construction if you want it on material, on whatever it is, based on the maturity of engineering. A lot of that, which makes the energy transition harder, is that a lot of it's just being done. And it's causing large scale delays, large overruns, and it makes it very difficult. So, good question though. Oh, this is the last one we have, kind of example we used in our Australia business unit. We had two almost competing projects on the same island. They're both doing cross cable installation. One followed kind of the principles we talked about in operational science. They did data planning. They did everything to help minimize variability. There's another project that didn't. They used the traditional P6 scheduling, working it, and this one here came in, you can see 10% under budget, and had a reduction in man hours. And so when we see reduction in man hours, it's cost, but it's also safety. More time you have to be out there in the field, the more opportunity you have for injury or safety incidents. And the other one I think was 10% over, 15% over.
Oh, yeah.
Must
Yeah, so this is as close to a controlled experiment as we have, right? Almost very similar scope, same location on the same island, same contractor even, just two different execution methodologies, and they got decidedly different results. In fact, the team that's under budget here has now been asked to go help this team try to finish the project.
And this is why it's hard. I mean, it's hard even within a big company, even one island. You get two different projects going, you get two different views, you get two different ways. Someone's being curious and wants to try something different. Someone says, no, I want to keep doing it my way and this is going the right way. And you get two different outcomes. So
Yeah, I'm going over there later this month to actually help them. And that's all, I think that's all.
That's all we have. What we ask is y'all be curious. You guys may know a lot of these principles, you may know a lot of these things. And say be curious and learn new ways of looking at projects and how to execute them and what you do with data and all these stuff. There's a lot of really cool stuff going on. I'm trying to transfer the way we execute projects. There's a lot of industries you can learn from like buildings, construction. They do it very, very well. A lot of things that even in the PPI organizations, they have a lot of different industries there that you can learn more about. PPI.org is a good resource if you want to learn more about this. And you can find Mark's screen in the backyard, but you can tell us in your conversation. You'll find out your
Yeah, I think Chevron is still, in the oil and gas world, I think we are still leading in this space, but our competitors are catching on.
Yeah.
But even then, if you guys leave A&M and go into the working world, you will probably one of the few people that are actually doing this. So this is kind of new stuff in the project management world. It's caught on way more in commercial construction, but heavy industrial, you'll be one of the few. But that will make you all the more valuable.
Reach out to us on LinkedIn, send us an email if you'd like to talk to us. Any questions? You guys happy?
I just had a question about what exactly are you
Oh. So we use a product called Semio. It's an off-the-shelf. You go on the internet and find it. In fact, I think A&M, they will give students a thing, a license if you don't already have one through A&M. You can go play it. Model, like I took it, I go to Cal Poly every once in a while and teach that like this, and we can go over to the Subway sandwich shop and we model the Subway sandwich shop. Anyway.
Who has a question here?
Oh, yes. So the model has to do with like the how many years, so what happens if only 7 years ago?
Yeah, so I mean, part of doing this, so part of the reason why you want to have short cycle times is so that you can react to things like that. So it doesn't necessarily solve the thing, right? Things will still happen. We want to try to understand and model that variability as much as possible. Things are still going to happen. But part of the reason why we focus on keeping that cycle time down is so that when they do happen, we don't have to wait 6 months to correct it. And also, we haven't started 6 months worth of things, and now we have to go change when change happens. So I don't know, that kind of answers.
And to help with that, I think Nick mentioned utilization of a source. You don't have actually a major change in the university, some of that variability, and then the day-to-day planning that we talked about at the end, that helps you identify. If you start identifying that on a daily basis, or at least not waiting 3 months to look at a schedule and then produce a monthly report, you know it on a daily basis, at least helps you start putting mitigations in place to get to eliminate that risk. Anybody in the back? Well, got sunglasses on your hat. You want to ask a question?
We didn't commend them on actually arriving on ring day.
Oh yeah, it's ring day. Congratulations, whoever got the ring.
Yeah. None of them are here. Well, thanks for letting us hang out with you guys.